In this video, we're going to go through net ionic equations, specifically in the case of a double replacement reaction. So the essential question that we're going to be answering is, how do double replacement reactions and net ionic equations show ionic changes, and why is balancing with coefficients important? All right, so every equation that we've written so far has been a molecular equation. So with a molecular equation, we have reactants and products and all of their states, just like that. Okay, so that's a molecular equation. A net ionic equation we'll talk about in a second, but let's just quickly review how to write a molecular equation. So first we identify the reactants, and on our left hand side we have silver nitrate and sodium chloride. So typically when we write a molecular equation, we identify the ions. We got Ag, we have nitrate, we have sodium, and we have chlorine. Okay, so we would identify the charges, and +1. Okay, since this is a double replacement reaction, the cation from compound 1 is going to go with the anion from compound 2. The cation from compound 2 is going to go with the anion from compound 1. Okay, and then we write what is going to happen on the product side. Okay, so all of those swaps ended up on the right side. Okay, now the states of matter come from this table. This is the official Flynn Scientific Common Ionic Compounds Solubility Table. So we would just match things up. So for example, we had sodium nitrate, so I would find sodium, and I would go down to nitrate. It says soluble, so that means that the state would be aqueous right here. Okay, so basically we went through all the steps right here. Our final step is to balance the equation. In this video, we're going to go through net ionic equations, specifically in the case of a double replacement reaction. So the question that we're going to be answering in this set of notes is, how do double replacement reactions and net ionic equations show ionic changes, and why is balancing with coefficients important? All right, let's dive in. So all of the equations that we've been writing have been molecular equations. Molecular equations show the reactants and products in their complete formulas without showing their ionic states. So when we've written these formulas out, we've started by listing out all of the ions. So I have silver, I have nitrate, I have sodium, and chlorine. I would go through and I would include all of the charges. Since this is a double replacement reaction, I'm going to draw my X. So silver will go with chlorine, sodium will go with nitrate. I would write out the right side of my reaction, and then our last step would be to balance it. So I would go through and I would list all of my ions. Okay, so 1, 1, 1, 1. Oh, look at this. It's already balanced. Okay, so I always want to make sure that we do that last check just to make sure that everything is balanced, because the atoms on the reactant side should match the number of atoms on the product side, according to conservation of matter. All right, so here are the steps that we went through. We identified the reactants, we determined the products. The formula that I showed was already complete, so I just went through the motions. Then we read out the formulas of the products, which we did, and then we finally balanced the equation. Okay, now on this equation we also have the states of matter, aqueous and solid right here. So those came from this table right here. So this is the official Flynn Scientific Solubility Table that we use. So the last species in our reaction was sodium nitrate. So to find that, I would have gone to sodium right here, and I would have gone down to nitrate. SOL means that it is soluble, and we represent that by writing aqueous. Okay, now silver, Ag, chloride, was insoluble, so we represented that with a S for solid. Okay, so when we're writing out our molecular equations, we want to include the states of matter because those are going to be important when we do our net ionic equations. Okay, so a complete net ionic equations shows all of the strong electrolytes, which are soluble ionic compounds, disassociated into their ions. So why are we doing this? Well, an ionic reaction, the way we write it out, will simplify complex reactions. So there's a lot of moving parts, and when we write out a net ionic equation, it makes it easier to see which ions are actually involved in the reaction. It also helps clarify the reaction mechanism. So again, when we see how the ions are moving around, this will really show what's going on with the reaction. Finally, a net ionic reaction helps us predict the reaction outcomes. Okay, so we're going to do an experiment where we'll see that you're going to take two things that are aqueous and they'll combine to form a solid. So kind of like the reaction that we had here, we had two things that were aqueous. Okay, so they're dissolved in water and it formed a solid. So again, writing out our net ionic equation will help us understand what's going on, and it's going to help us predict what's going to happen with the reaction. Okay, so here are the steps to write out a net ionic equation. Okay, very similar to what we were doing before. We're going to identify all soluble compounds. So we're going to be using this table right here. Anything that's soluble will dissolve into ions. Anything that is solid will remain in their molecular form. Okay, so anything that is not aqueous will remain in its molecular form. Then we're going to write each soluble compound as its ions. Okay, now ions that are not involved in the reaction we call spectator ions. So spectator ions again are not involved in the reaction because they're just kind of hanging out. They don't really do anything. Just like the spectators at a baseball game or a football game. As much as they think they're involved in the game, they're actually not. So spectator ions in a reaction don't really do anything. Okay, so let's take a look at this example. It says convert the molecular equation to a complete ionic equation. Okay, so anything that is aqueous, we are going to separate into its ions. So I have silver, Ag. We're going to carry down the state of matter. We have nitrate. I also want to include charges on everything. We have sodium. And again, we're carrying down all of our charges and our states of matter. We have chlorine. Okay, now on the right side, our silver chloride is a solid. We just bring that down as is. We don't break it apart. And then we have sodium nitrate, so Na. Okay, so there is our complete ionic equation. Okay, so next what we're going to do is we're going to go through and we are going to cross off anything that exists on both sides. These are our spectator ions. So let's see, silver exists on both sides but not in the same state. So I'm going to leave that alone. Nitrate exists on both sides as an ion, so I'm going to cross that off. Sodium exists on both sides as an ion, so I'm going to cross that off. Okay. Chlorine exists on both sides, but not in the same state. Okay, so I leave that alone. So now I'm going to rewrite it. So this is our total ionic equation. Our net ionic equation is everything that's left over. So I have silver. I have chlorine. And that forms silver chloride. solid. Okay, so that's our net ionic equation. Now my spectators are the ones not involved in the reaction. So that would be nitrate and sodium. That's it. So again, our molecular equation, let me just label this one. Our molecular equation is the one where everything's put together. It's the one that we're used to. Our total ionic equation was writing out every single ion. Anything that was aqueous, we broke apart into its ions. Our net ionic equation was the leftovers. So anything that was not crossed off on both sides, anything that was not a spectator, that's the net. And then we listed our spectator ions, which are the ones that we crossed off, which were on both sides in the same state. They weren't doing anything. Okay, let's take a look at this equation. Okay, so this one's going to be a little different. So we have some coefficients, and we also have some subscripts. Okay, so with net ionic equations, we are going to do something with these that's a little different. So again, this is our molecular equation. So our first step is going to be to go through now, and anything that's aqueous we're going to break up. Okay, so let's start with our first compound right here. So we have sodium sulfate. The 2 that is next to our sodium is going to pop out in front. So I'm going to bring that out in front. So it's going to be 2 sodiums. We have sulfate, SO4. Okay, what do we have next? We have barium, Ba. Ba is +2. And then again, we have a 2. That 2 is going to come out in front of our nitrate. Okay, now we have a coefficient. That coefficient is going to go to both pieces when we write them out. So it's going to be 2 sodiums and then we have 2 nitrates, and then finally we have our solid barium sulfate. Okay. Anything that exists on both sides, we cross off. So I have 2 sodiums. Let's cross that off. I have 2 nitrates. And that's it. So now we write out our net ionic equation. Our net is anything left over. So we have sulfate. I have barium. And that is going to form barium sulfate. Our spectators are anything left over. So that would be our sodium and our nitrate. And that's it. So we went through how to write out net ionic equations. Again, we start with our molecular, then we wrote out our total ionic, then we wrote out our net ionic, and then we named our spectators. That's the process.